Okay, so question three, this is about four solid steel rods, each of length this and area this, blah, 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 and equally support weighing 10 kilonewton object. That means, let's say this is the object which is 10 kilonewton, and then there are four steel rods which supports this weight of 10 kilonewton. So the weight of the object causes the rods to contract by this much. That means they basically compress. That means the extension or the change is 0.10 directly given. That is important. What is the Young's modulus? So equation is very easy then. Formula for Young's modulus is Fe over A times L. Now the force is going to be 10 kilonewton divided by 4. The important thing is since 10 kilonewton is not supported by a single rod, 10 kilonewton is supported by four different rods. So you have to divide 10 kilonewton by 4. So you'll get the force in one of the rods, right? So that would be 10 exponent 3 divided by 4. That's the force. That's F. Extension is 0.10. So 0.10 exponent minus 3 millimeters over area, which is basically 250. And since it is in millimeter square, you have to convert it into square meters. So that is going to be minus 3 and minus 3, which is minus 6, right? And then length. The length is 2.0 meters. So once you solve this, what are you going to get? So basically, you are going to get 2 exponent 11 Newton per meter square or pascals. So that's B. Question 4 says, what is represented by the gradient of a graph of force and extension? So force here and extension here. So the gradient here would be basically K because according to Hooke's law, K is F over E. So spring constant, that would be B. Okay, let's try question number 5. So the question 5 here, it says that a student is investigating the mechanical properties of a metal. Okay, well, I see a stress and strain graph. And then they say the student repeats the experiment with a wire made of same metal. Okay, with twice the original length and half the diameter. So now the important thing is they are basically giving us a graph of a stress and a strain, right? So the gradient of this is going to give us Young's modulus, right? So Young's modulus is a constant which is basically not dependent upon the length, diameter, area. It is only dependent upon the metal, what structure that metal does have internally, the metallic bonds and things like those. So if they say that this is for a given metal, so the ratio of stress over strain, let's read it over here. So stress here is 4 exponent 6 and strain here would be 35 exponent minus 3, right? So that's the ratio of stress over strain. So this should stay constant regardless of the length made twice and diameter made half. Why? Because spring constant is something that can change with changing the diameter of the spring, changing the length of the spring. So that is dependent upon the dimensions originally. But Young's modulus was derived in this manner so as to have a constant of material, not on dimension. So if Young's modulus is there, that means regardless of the length of the pipe or the material or the diameter of the rod, it has to have the same Young's modulus. So let's see which of these graphs gives us the same answer. So, well, this is not 35. This is 4. This is 16, right? So 16 over 65 is not going to be the same ratio. 4 over 35. Yeah. So that's the answer here. So I'll go with B, right? Because it is having the same spring constant. Let's see what the other question is all about. Okay. So this deals with a composite rod. Okay. So glass, plastic, and nylon. Okay. Greatest tensile stress that can be applied to the composite rod before it breaks. So someone is basically kind of pushing this rod, pulling this rod. So the force here is tension because this is going to try to expand this. So the composite rod will break when it's total extension. That means the total extension, if it is 3 exponent minus 3 meters, then it is going to break. So the total extension will have some extension of the plastic rod and that of nylon rod, and that should be 3 exponent minus 3 meters. Okay. So now I have to find out the extension of the plastic rod. So, well, they have given us the Young's modulus. Let's use Young's modulus. That's the stress in plastic rod over strain in plastic rod. Okay, and then if we say we have Young's modulus of the plastic rod, which is 40 gigapascal, which would be exponent 9. So stress is not there. And here we have the strain. So strain is change in length per unit original length. So I saw this. Yeah, so that is there, right? That's a clue here. So we can work on strain. So strain is maybe extension in plastic over original length, which is 1. So that's 1, right? Let's do it here like 1. So that would be 40 exponent 9 times EP equals to sigma P. So EP would be sigma P over 40 exponent 9, right? So in the same manner, the extension in nylon should be stress in nylon over Young's modulus of nylon, which is 2 exponent 9. Yeah. So now we can have the total tensile stress. So the one important piece of information I'm going to see is, okay, so the stress here should be same. Reason is they're going to apply a tensile force on both of the sides. So stress essentially stays same here, right? So let's substitute these values here. So if you plug in these values here, so we are going to have sigma P over 40 exponent 9 and sigma n over 2 exponent 9 equals to 3 exponent minus 3. So let's replace them with x because that's what we are working for. The stress is because this complete rod is subjected to same tensile force and stress is about force per unit area. So basically they're subjected to same force and they do have the same area, right? So they're going to have the same stress. So we can just substitute it as an x. So now the only thing that's left is to find out x in this equation. So we can do it here. So this would be x, and that would be 1 over 40 exponent 9 plus 1 over 2 exponent 9 equals to 3 exponent minus 3. So let's find this x out. So that would be 3 exponent minus 3. Okay, let's do it. So 1 divided by 40 exponent 9 plus 1 divided by 2 exponent 9. Sorry, 1 divided by 40 exponent 9 plus 1 divided by 2 exponent 9. So the answer to this whole thing is 5.25, which there, when shifted to right hand side, has to be divided. So 3 exponent minus 3 has to be divided with the answer. So I'm going to have 5.71 exponent 5.71 exponent 1. So 6, 5.71 exponent 6 Pascal. So this is going to break it. So maximum stress, 5.71 exponent 6. So the answer here should be, this is, yeah, this is C. So this would be C. That would be 5.7 exponent 6 pascals. So we are going to select this as the answer. This is way more than the stress it can handle. And this is not the maximum stress. These are way too small. So the closest option is C, right? Let's see what the next question is about. So question number 7, it says that a spring balance consists of a spring of length 20 centimeters with a hook attached. When a fish of mass this is suspended, the new length is this. The spring constant, so quite easy. So K is equals to F over X. So force is 3 times 9.81, right? And extension would be 27 minus 20, which is 7 exponent minus 2. So let's see, what do we have here? So 3 times 9.81 divided by 7 exponent minus 2, 420 Newton meter. So that's D, doctor. So question 8 tells us here that there is a graph of shows the effect of force. Okay, we can see that. The spring obeys Hooke's law. Well, we can see that. So what is the total extension of the spring? Okay, so they want us to find out the extension when 7 Newton force. So the graph only tells us about 5 Newton. Okay, so if it obeys Hooke's law, then F is equals to KE is valid, right? So let's find out K here. So that would be F over E because spring constant stays constant up till it applies Hooke's law. So if even if we go beyond 5, 7, 10, whatever, so spring constant would be same, right? So let's first find out the spring constant for this. So force is 5 Newton and extension from 11 to 14 is basically 3 centimeters. That's 3 exponent minus 2. So the spring constant we are going to have is 166.7 Newton per meter, right? Now, they want us to find out the extension. So the formula for extension would be force upon spring constant. So the new force is 7 Newton and spring constant, which stays same even at force of 7 Newton. So this gives us 0.042. So which is in centimeters. So let's multiply it with 100. So we're going to look at 4.2. That's A. Question 9, extension force graph is there. Okay, well, we can see that. What is the spring constant? So 6 divided by 15 exponent minus 2. So 6 divided by, 15 exponent minus 2 is 14. So that's D, doctor. And these are kind of now easier questions. So let's try question 10. It says the stress strain graph for a virus shown. Stress is this, strain is this. So that's basically Hooke's law. That's not Hooke's law. What is the Young's modulus? So Young's modulus would be ratio of stress over strain. So quite easy. Stress is 2.1 exponent 8 over strain is 1.4 exponent minus 3. So this gives us option D. Question 11 states a metal wire is fixed at one end, the length L and cross-sectional area A. Wire extends E when M is hung. What is an expression for Young's modulus? So expression would be force times length over area times change in length. So since it has a mass M, so the force would be mg, right? And original length, they say it's L, it stays same. And A is A, E is E. So mgl over A, E, mgl over A. Yeah, that's B, right? So question 12 states that a zero point 0.8 meters length of steel wire and a 1.34 meters length of brass. Okay, the combined bars are suspended. Okay. The Young's modulus are given, cross-sectional area is same, the wires extend. Okay. So what is the total extension? So total extension would be extension of the steel wire plus extension of the brass wire. Okay. So steel wire has, we have, well, the Young's modulus for steel. So that would be force on steel, original length of steel times area of steel and extension of steel. So that's what we have to find. So if let's say extension is equals to force times length over area times Young's modulus. So let's plug in the values. So force is going to be 40 Newton because it basically experiences the same force because force here would be force here and then that would be force here and that would be force here. The force is same. Length of the original wire is for steel, it's 0.80 over area of the steel wire and both is same. 2.4 exponent minus 6 times Young's modulus is 2 exponent 11. So let's see the answer. So that's 40 times 0.80 divided by 2.4 exponent minus 6 times 2 exponent 11. So what do we have? We have 6.6 exponent minus 5. That's the extension of the steel. Using the same equation, we can find out the extension of the brass. So what's the force? 40. What's the original length? 1.4. What's the Young's modulus? That's 1 exponent 11. And what's the area? Area is the same thing. So that's 2.4 exponent minus 6 times the Young's modulus, which is 1.0 exponent 11. So let's find out the answer here. So what do we have? We have 40 times 1.4 divided by 2.4 exponent minus 6 times 1.0 exponent 11. So this comes out to be 2.33 exponent minus 4. 2.3 exponent minus 4. So we can add these up to find out the total extension. Let's see if I add this with my original answer of 6.6 exponent minus 5. So I get 2.9 exponent minus 4. Exponent minus 4. So that would be B. That's almost 3. So the next question is about a metal cylinder is able to withstand a compressive force of 4 kilonewton without deforming plastically. Okay. The cylinder has a cross-sectional area A and would be R at the elastic limit when the stress sigma elastic limit. Okay. What is a possible value, pair of value for A and sigma? So say we have a force and extension graph. So we'll have limit of proportionality, then elastic limit, and then plastic. Okay. So they want us to find here at 4 kilonewton, it can withstand without, being deformed plastically. So we have to find out a pair of values of A and sigma that would be R its elastic limit. So that's the elastic limit, and it can withstand, more force than this. Okay. So find out the values for a pair of. So we should look at an answer of force which they can give us to be more than 4,000, because right now it's somewhere here. That's 4,000. So it's more than that. Okay, let's find this out. So simple is sigma is stress is force over area. So sigma times area is force. Wow. So that's a simple answer then. So we have to just find out the answers for all of these and see where it goes beyond 4,000. So I'll start up with A and D. So that saves time here. Let's see. So first A, 1.5 exponent minus 5 times 50 exponent 6. Yeah, well, that's 75 something. So exponent 6 is going to be 750, right? 750 is very, very less than 4,000. So less than 4,000. So not okay, not okay, not okay. Let's try D. So that's 7.5 exponent minus 5 times 80 exponent 6. So that's 6,000. Well, see, that's less than 4,000. So I'll go with D. D is the correct answer.